Okay, so we're going to finish up the analysis. We got really close to the end on the last lecture, but I want to show you the final touches on this analysis. So we'll just quickly review. So with analyzing the HCl spectrum, we went through and we assigned the different branches. We went through assigning their quantum numbers. We had the V double prime to prime, so we were doing a fundamental transition for HCl, that ground to first vibrational excitation state. And then we had the rotational lines on top of that. So we had the energy equation, and then I'm just going to swing through this. We had all of those transition equations. We had the Q branch, we had the R branch, the alpha term, the rotational constant, the centrifugal distortion constant, lots of algebra, the P branch, the P branch centrifugal distortion term, and then we were able to assign all of the little transitions. So when we assign these, remember, these are quantum number assignments. So we're actually assigning the quantum numbers, but you know, when we have an R1, that definition of R1 is telling you that you're going from the ground vibrational state of 1, and R is telling you it's delta J plus 1, so it's going from 1 to 2. Okay, so the R is actually telling you what delta J is. If you have the P branches, that P is telling you what delta J is. It's telling you delta J is minus 1. So if you have the P2 line, you're at level 2 in the ground vibrational state and level 1 in the upper vibrational state. So V is changing and J is changing. We have these equations which would give us a regression, but we have two regressions if we analyze the P and R branches separately. So we made up a quantum number. We said, for the P branch and the R branch, let's change from J to M. And we swung the P branch over to the negative side. And so R, for the R branch, we slid it forward 1 J value. So M is J plus 1. And the P branch, we made minus M values. So M is minus J. And then now we don't have a value at 0. That value at 0 is our vibrational frequency. Okay.
So that MJ plus 1 is for the P branch?
No, that's the R branch. The J plus 1, the R branch slides over 1 quantum unit, and then the P branch, it goes to the negative side so that we can get one linear regression with negative values and positive values, and the intercept where it crosses 0 is the vibrational frequency. Okay, so that's our M value. We call it the running quantum number, but it still has the word quantum number in it, and I don't like that because it's really not a quantum number because we have these negative quantum numbers. And so what I end up calling it is the fake quantum number. Okay, it's really just because we want to do the regression analysis. All right, so then we talked about linear least squares fitting, and we do the multiple linear regression where we had the 3 regression columns, and the Y input are the frequencies. Now we're going to use this technique again in the next analysis that we do, where we do combinations and differences. So here's how we do the regression. We have the data analysis button, and we click that. If we don't have it, this is the procedure for getting it. Then we do regression, and then we have the Y input values and the X input values. So the independent variables are the quantum number variables, and the coefficients of each of those quantum number columns is what we're trying to model. And so then our Y values are always the frequencies and wave number. So here's our output. We have some impressive statistics. And so we're talking about these p-values, and this is pretty much where we ended, I think, talking about the p-values, the significance of these p-values. Remember, this is the probability that the null hypothesis is true. So this is a really small probability, 10 to the minus 105. Okay. And that's because of 2 reasons. One, our number, again, the null hypothesis is that vibrational frequency is not statistically different than 0. Okay. And here it is at 2,885. Now, that could still be not statistically significant from 0 if our uncertainty was 4,000 or 3,000. Okay, and sometimes you have that. When you're doing peak areas, in chromatography, and your peak areas are 102,000 and 304,000 and 500,000 peak area units, and your intercept is maybe 8,000, and your p-value for your intercept is above 0.05, meaning it's not statistically different than 0. And you say, how can 8,000 essentially be 0? Well, if your values are so large, 500,000, 400,000, 300,000, and down here it should cross 0 and it's crossing at 8,000, well, it's 500, 300 something, and 8 is what you're talking about. And it's saying in that model, that's really not statistically different than 0. So if that happens, you redo the regression analysis and you click this button right here. So if that p-value is greater than 0.05, then you redo the regression and you click this and you say that constant is 0. Okay, and so then it won't model that intercept. It'll just model the coefficients of each column independently, and it'll set the intercept to 0. Okay. Well, we're not anywhere close to that. We have an enormously small, I would say, a minuscule p-value for our intercept. And even for our centrifugal distortion, this is the most uncertain one. We still have a very nice p-value, a 10 to the minus 35, so it's very good. And so our confidence is 1 minus p. So this was, 99.999. Okay, times 35, right? That's how confident we're pretty sure. 35 nines on that.
You're saying there's a chance.
There's a chance. That's right, Jim Carrey. So you're saying there's a chance. Yeah. And so then we can calculate R. So once we have those B values, we can use the rotational constant to calculate our bond length. So this is exciting because we're calculating the bond length for HCl using a spectrum. So we don't have a ruler that can measure down to the angstrom level, okay? But we use spectroscopy and we can pull these physical constants out. Now, this is the calculation. If we want to use our reduced mass in grams per mole, right, we have 1 gram per mole for hydrogen and 35 grams per mole roughly for the chlorine. That's convenient, but we need to get out of grams per mole and into kilograms and everything so that all the units cancel. The per mole requires Avogadro's number. Okay, the grams requires a gram to kilogram, and the kilogram is going to work with Planck's constant here. Okay, then we have, we're dealing with bond length. We want that in angstroms, but it's going to be angstrom squared. And so this is 10 to the 20 angstrom squared per meter. That per meter squared cancels with Planck's constant. Then we have Planck's constant divided by the speed of light, so the per second goes away. Let's see, what do we have? And then our BE value is in wave numbers, okay? And so this has got centimeters to the minus 1. So we can rearrange all of this and we can solve for this bond length in angstroms. So this is a whole lot of mess. We could use Excel, of course, and that's not a problem, put all those numbers in. But if we were doing this by hand, then we would just consolidate all of those constants. And I just wanted to show you this because it's such a useful skill. You can make up your own constant, okay, that has the units that you want. None of those things change. Angstroms to meters isn't going to change. Avogadro's number, Planck's constant, speed of light. So you can put all that stuff into one constant, and only those variables that you're interested in do you leave as variables. And always leave yourself a reminder for the units, right? Include your units. And so it's important to use all the significant figures for your calculations. So here's Avogadro's number. I got these from NIST, okay? Here's the speed of light. It's defined, okay? It's defined to here in meters per second, but we're in centimeters, so we have an extra 100. And then this is Planck's constant. Normally we write 6.626, but there's 4 other digits on Planck's constant. So include all of those so that you're not introducing uncertainty with your constants. If we do all of this peak picking and it's really tedious and so on, and we analyze the spectrum, and then we only use 4 significant figures in our constants, we're really screwing things up. Okay. Notice in the previous regression, here we've got our vibrational frequency, and we're certain out to the third decimal place. So we have 7 significant figures. Remember, significant figures are all the certain digits plus one uncertain digit. And so how do we know where the uncertain digit is? Here's our standard error. And so that's telling us this is our uncertain digit. It says it's 8, but it could be 4 higher or 4 lower. You know, it could be 4, it could be 12. Make sense? And so that's our 7 significant figures for our vibrational frequency. Why would we then use Avogadro's number using only 5 digits, or Planck's constant using only 4, or speed of light using only 1, 3 times 10 to the 8? You know, so we want to use all of those significant figures whenever you're doing real work from your constants. Okay. And then if we've calculated the vibrational frequency, we can calculate the force constant.
Isn't the V not come off of the regression?
Yeah, so we have this, and this is the equation. So I'm just saying we need to invert that, you know, and calculate the force constant. So you just switch that around algebraically. And so then we can do this. Now, if we look at the units, okay, our centimeters here, our wave numbers cancel with the centimeters per second in terms of the speed of light. And so we end up with per second here squared. And so our units are kilograms per second squared. But this is newtons per meter.
So multiplied by 1 meter over 1 meter.
Yeah, you already got it. Yeah, so he's giving away my secrets. Okay, so how do we get to Newton per meter? Okay, so if we just multiply by 1, a meter over a meter, then this piece right here is a Newton. Mass times acceleration, right? And Newton is a force, and F equals ma. Mass times acceleration is a Newton. And then per meter, we're stretching that bond. And so it's how much force it takes to stretch that bond a meter. And so these are the 2 equations you use to do the derived constants. And so you'll derive the bond length from your rotational constant and derive the force constant from your vibrational frequency. Now let's look at the uncertainty analysis. We're going to get into propagation of uncertainty. We have BE plus or minus, and I'm going to use this term SBE. Okay, so that's the uncertainty or standard deviation of BE, which we get from the regression analysis. And we want to solve for RE, and that's easy. We just do this algebra and we solve for RE. But we also need to know the uncertainty in our bond length. That is not in the regression analysis. So what's going to be our uncertainty? How many sig figs do we have in our bond length after we do this calculation? And that's why we need to know how to propagate uncertainty. We have uncertainty in BE that we get from the regression analysis. How do we get the uncertainty in the RE value? Okay, that's what we're going to do. Okay. Now this is a multiplication and division system, and so I'll go ahead and write out the equation here. If we were to take SBE over BE, that is called the relative standard deviation. I'll go ahead and put BE in as a little subscript. Does everybody understand what I'm doing? I'm taking the uncertainty and dividing by the value. Pretty straightforward, okay? Now here's a nice thing. For multiplication and division, for this situation, I'm going to run out of space here. Mult, divide, systems. I'll just write it over here. Hopefully you have more space on your paper than I have on my screen. And I'll write it for, say, y equals, say, mx r s d y, is equal to the sum of all the pieces inside my equation. So if I have, let me erase that. So if I have different pieces, like I have an X and I have a Y, so my RSD for my Y value is equal to RSD for X plus RSD for M. And I think those are squared, aren't they? Let's see. Yeah, squared. These are all squares. Yeah. I'm going from memory. Okay. And so that's how I propagate these uncertainties. And same thing here. So I have this equation. If I have uncertainties in my nu zero value, okay, so I have S nu zero over nu zero. How is that related to this K value, right? S K over K. I know this value, I know that value. I can solve for K, and so I have one equation and one unknown. I can solve that. So we're going to do that next. We have these standard errors here. And from these, from BE, we were able to derive the bond length right here. And from nu zero, we were able to derive the force constant here. So we take these, we go to RSDs for nu zero, then we get RSD for K, then we get S for K. Once we have S for K, then we can calculate this 95% confidence intervals. So these 95% confidence intervals take that average value plus or minus some range that's going to capture 95% of this uncertainty curve, okay? And this Z95 is 1.96. So because we're doing a large linear regression, we can use population statistics. We don't have to get into the student t-values and the degrees of freedom or anything like that. We can just say that we have a population, and this 1.96 captures 95% of the normal distribution. So we've taken that uncertainty in K, and we've said we've multiplied by 1.96, and that's this value right here. And for the BE, we did the RSD for BE. We converted that to the RSD for the bond length. Then we found the uncertainty for the bond length times 1.96, and that's what gave us this reported value here for the bond length. Now, the convention is to keep one uncertain digit, but you can see in the literature a lot of times they keep two, just to kind of show you what that second digit of uncertainty would be. And so for following that convention, I kept 2 digits of uncertainty. Okay, so my uncertainty, the standard deviation times that Z95 value, is what is telling me where to round. That's the important point. Right? How do you know where to round your values? You've got to know where the uncertainty is. So after you're finished calculating the uncertainty, that tells you how many digits to keep. Okay? And look at how many digits we keep. It's amazing. So we have now, with 2 digits of uncertainty, 8 values in our vibrational frequency, 7 values in our rotational constant. Our vibration rotation coupling constant is known out to at least this is the tenths, hundredths, thousandths, 10,000ths, 100,000ths place, okay? The centrifugal distortion constant, we have 2 certain digits and a couple of uncertain digits. That's amazing. And then this one just floors me. This right here, this is 1 times 10 to the minus 10 meters. Okay, think about what we're measuring. We're measuring something that is 10 to the minus 10 meters, and we're certain out to the minus 11, 12, 13, 14, 15, we're certain out to the 10 to the minus 15 distance length from this analysis. That's amazing. I mean, I can't do that with my yardstick or my meter stick right here. And here I'm barely certain, you know, this is 10 to the minus 3 meters, a millimeter, okay? And I can go to half a tick mark. So my uncertainty is really in that, you know, 10 to the minus 4. And here we're at 10 to the minus 15. That's where our uncertainty is. Our tick marks are 10 to the minus 15 meters apart in analyzing this spectrum. I just kind of like to sit here and think about that, you know, instead of just throwing the numbers up on the screen, saying, yeah, the bond length's 1.274821 angstroms, to just kind of think about what that is telling us and how sure we are. That's amazing. Yeah. And then the force constant too. It takes 480 newtons to stretch this bond a meter. You're not going to be able to stretch it a meter, but if you were, if this spring didn't break, right, you'd take 480 newtons, you know, which would be, again, you know, I guess divided by 9. Anyways, definitely over 100 kilograms. It could hold up 100 kilograms, this bond, this one little bond. Okay. So anyway, these are our confidence values. Let's look a little bit more detail on this propagation of uncertainty, though. Oh, and also, how did we do? Let's compare this to the literature. It's close, but there's definitely something, I won't say wrong, something different in our analysis versus what the analysis was done for the literature values. We're very certain of our values, okay? So our values are incredibly precise. But here's our literature value, 2885.32, and is that within our range here? So, like if it's lower than our value, so if we subtract 86 from this, okay, that knocks out the 82, and maybe even takes 1 off of this, so 87, right? And this is 32, and so we're high. We're coming in high by, you know, about half a wave number. Half a wave number is huge compared to our uncertainty, right? So if we just round this up to 1 and we're off half a wave number, we're 50 times our uncertainty off. So yeah, question mark on that. We're biased high. What about the rotational constant? Yeah, 58, 59. I'd have to get in here and like subtract that from 94. It doesn't change 588. So yeah, so we're coming in low on this one. So we're high here, low here. And if you think I'm building up to something, I'm not. I'm just looking at it and saying, okay, I don't know why we're off on these. So this does show you the example, at least, of the difference between precision and accuracy, right? That's our data. We're off target, but we know exactly every time we shoot, we hit the same spot, right? Our analysis is off somewhere, and it may be the calibration of the actual spectrometer is off. So we would need to go and check the calibration of my laser wavelength, which is actually calibrating my interferometer. Okay, this is telling me I have a very consistent bias. Okay, it doesn't tell me my results are garbage. They're very precise, but they're biased some way. Okay, and I need to figure out how to get that dialed back in, because I think if we get the spectrometer calibrated just right, then all of these values will fall right on the literature value. Okay. Now the literature value, just as a note, the literature reported nu E. Okay, so if you look up a nu E, you get this value here. Okay, and if you look up in the literature values, you get XE. And so you get this value here. And remember when we did our transition equation, we took these two pieces and brought them together to make new zero. And so that's why we need to actually compare apples to apples. And so we had to compute this literature value using these other two literature values. So if you were to go to this CRC and you're trying to compare your values for new zero, and you look up the vibrational frequency, you're going to get 2990. And it looks even worse, right? There we're off, several wave numbers, whole wave numbers. And it's because the literature is giving you new E, and we're calculating new zero or measuring new zero. Okay, so let's go into detail on the propagation of uncertainty. So that's the next set of notes.